Hi, welcome to educator.com. We're going to be talking about hypothesis testing today. All right, so the first thing we need to do is sort of situate ourselves. Where does hypothesis testing fit in with all of inferential statistics? Then we're going to talk about how to actually create this hypothesis that we're going to test. And that hypothesis is really going to be about a population. And when we say about a population, we mean really about population parameters. And there's actually two parts to any hypothesis that we test. There's the null hypothesis and the alternative hypothesis. And we're going to talk about how those fit together. Then we're going to talk about potential errors in hypothesis testing, because it's good to know going into it. Finally, we're going to end with the steps of hypothesis testing. And we're going to do the steps of hypothesis testing when sigma, the population standard deviation, is given, and when it's not given. And if you have just refreshed yourself with the confidence interval lesson, you can probably guess that when sigma is given, we're going to be using z distributions or normal distributions, right? Normal. And when sigma is not given and we have to estimate the population standard deviation from the sample using S, then we'll use t distributions. And remember, in order to use the t distributions, we're going to need to figure out the degrees of freedom. Okay, so let's go back and situate ourselves with all of inferential statistics. So basically, the idea of inferential statistics is that we use some known populations to figure out the sampling distribution. And the one that we're using a lot is the SDOM. We are going to use some other ones later. So we figure out sampling distributions, and then we want to compare a sample from an unknown distribution. We want to compare a sample from that to this sampling distribution. If this sampling distribution says, hey, this sample is very, very likely, then we might say, oh, then maybe this sample, this unknown population, is very similar to this known population. But if this sampling distribution sort of tells us, wow, this sample is very, very unlikely, then what we might think is, well, then we could rule out this known population as a potential candidate for this unknown population. Now, in doing all of this in inferential statistics, there's sort of two issues that come up. What happens when we don't know what the population looks like at all, right? And we want to sort of try to figure out where the population mean or different parameters of the population might be. Well, in that case, we use confidence intervals. And when we use confidence intervals, we try to figure out where mu is from x bar. So another way of thinking about it is we try to figure out something about the population from the sample information, right? Because we have that sample information. Another thing, another tactic we could take is that we could use this idea and say, well, how do we decide when a sample is unlikely? How do we decide when to draw this little x, right? When do we decide, like, oh no, this guy is really weird, right? Well, in order to do that, we now have to learn about hypothesis testing. And now the goal of hypothesis testing is going to be slightly different from a confidence interval, yet related. It's sort of the flip side of the coin. Basically, you're going to try to figure out whether your x bar is unlikely given a hypothetical population, right? Mu. So in this case, what we're doing is we're setting up a population. So now it's like the population is sort of stable. And then we're going to compare the sample to it, right? So here's our sample and here's our set standard, right? And so here, the population is sort of moving, well, not moving, but this is the target, and this is what we use to, get that target. Here, this is already set, and we're comparing this guy to this guy, right? So, so in this way, you need both confidence intervals and hypothesis testing to sort of give you the full story. Now, you might also hear that hypothesis testing, another word or phrase for it will be a test of significance, a test of significance. Now, a lot of students misinterpret that to mean a test of importance, right? Because that's the modern way the word significance is used. But that's not actually what we're talking about here. When we call this a test of significance, this was actually a word coined in the early, this is actually using the meaning of significance from the early 20th century when this test was actually invented. So back then, significant just meant prominent or standing out, right? So I like to think of it as being weird, right? Like how much does this sample stand out? Is it significant? Is it prominent and different? Or is it very, very similar, right? And so those are the two ways you could think, those are the ways you could sort of think about it. I don't want you to think of it as a test of importance. Okay. All right. So now that we know why we need hypothesis testing, how do we hypothesize a population? How do we make up a population? Do we have to make up all the individual members of the population? I mean, what do we got to do, right? Well, here's the thing. We could assume some things about population parameters and then test those assumptions. We don't actually have to simulate every single member of the population. We could just make some assumptions about parameters. So in order to set up a hypothetical population, you set up a parameter. For instance, you say mu is equal to something, right? That's how you set up a population. Then check whether our sample is likely to have come from such a population, right? And so in doing this, we need to figure out how do we hypothesize sort of rigorously, right? With, so that we could get as much bang for our buck from our hypothesis. Well, in order to do this, we have to have two parts to our hypothesis, and this is going to make our hypothesis better, trust me, but I'll explain to you as we go. So the first part of the hypothesis is what we call the null hypothesis, and null means, null is frequently used to mean like zero or not important, or even like the default, right? The null hypothesis in this case is your hypothetical population. For instance, and we write the null hypothesis like this, H sub 0 or H sub naught, H naught, right? So we might say mu equals 0, right? Ta-da, we have created a null hypothesis. Now, I've just made up this 0 right now. There are better ways of doing this, and we'll talk about those later. So here, we could also write this as, in terms of things like standard deviation or other things, but frequently you'll see the mean being the hypothesis of this population. Now, the alternative hypothesis is, what do we learn if this is not true, right? So if we rule this out, then what have we learned? And in that way, these two make up the full hypothesis. If we find this, then we learn this. If we don't find that, we learn this other thing, right? And what we learn if this is not true is at least that mu does not equal 0. Right? So this is called the alternative hypothesis. And this helps us at least figure out something when we don't figure out this, right? So if we don't find this to be true, at least we find this to be true. If this is not true, then we at least find this to be true, right? Vice versa. Now, these two hypotheses together, this is more powerful than just having one hypothesis alone. And we'll talk a little bit about why. And it goes back to that idea of the test of significance. Hypothesis testing, or the test of significance, really is a test of weirdness. It tests how weird the X bar is, right? So this is the question that it can answer. Is the X bar weird? Is it different from this population? But it can't actually tell you, is X bar very, very similar to this population? That's not what number it gives you. It only tells you how weird it is. It doesn't tell you how similar it is. Those two are actually not flip sides of the same coin, right? And so because of that, we actually, our goal here in all of hypothesis testing is we actually find out the most when we reject the null hypotheses. That's actually when we find out the most. I mean, this might not seem like we're finding out a lot because it's like, oh, great, we ruled out 0. There's like an infinite number of mu's that we now need to test, right? But actually, in hypothesis testing, what you want to do is reject the null rather than accept or fail to reject the null. Just because this is set up as a test of weirdness, that's really the only thing you could find out. It's true that it would be nice if we could find out more than that, but that's the limitations of this hypothesis testing. It's a limitation, but it's sort of also like a fact of life too, right? Because even though it's a limitation, this hypothesis testing is still a powerful tool. But it's good to keep in mind that this is one of the limitations. Okay. So a little bit more about these two hypotheses. Now, these two hypotheses, the null and the alternative, sometimes you might see the alternative written as H sub 1. They must be mutually exclusive. This means if one is true, the other cannot be true. If the other is true, the first cannot be true, right? So you can't have a null hypothesis and an alternative hypothesis like mu equals 1 and mu equals 2. They're not mutually exclusive. If one is false, the other one doesn't have to be true. It could be true, but it doesn't have to be, right? Whereas mu does not equal 1, mu equals 1. Those are mutually exclusive. If you rule out one, you absolutely know that the other one has to be true. Also, together, they must include all possible values of the parameter. You could think of the parameter, such as mu, on a number line, and you need to cover this entire number line. So you could have a null hypothesis like mu is greater than 0, right? So if this is 0, right, you might say, you know, mu is greater than 0, right? But then your alternative hypothesis has to be mu is less than or equal to 0, so that you color that in and color all of that in too, right? Because that way you'll cover the entire space, the parameter space. If these are both true, here's what you get. One of these two hypotheses must represent the true condition of the population. You find out something that's true about the population. And then, as we said before, typically in research, your goal is to reject the null and find support for the alternative hypothesis. You can't actually prove the null hypothesis, but you can reject the null hypotheses. And the whole reason is because hypothesis testing is a test of significance or a test of weirdness, how much this X bar stands out, right? So you can only tell me whether it stands out a lot from the population or not. But you can't tell me, oh, it's probably really, really, really similar to the population. You can't tell me that part. Now let's talk about some errors that we could potentially make in hypothesis testing. There are some foibles you need to watch out for. Well, first, it helps to sort of imagine that there are two potential realities, and we don't know which one of them is true. Not when you do statistics, at least. One is that the null hypothesis really is true. It's actually true. We don't know it yet, but it's really, really true. The other possible reality is that the null hypothesis is false. Your sample didn't come from that population, right? So those are your two possible realities. Only one can be true at any given time. You can't have both the null population being true, the null hypothesis being true, and false at the same time. You got to either have one or the other, right? So these two boxes, right? So this one and this one have to add up to 100%. But these two boxes, this one and this one, have to add up to 1, right? And that's because we have a 100% possibility of this being true and a 100% possibility of this being true. If this is true, this is just not true, right? Okay, so given that this is reality, but we don't know reality, what's the deal? How do we put that together with hypothesis testing? Well, when we do hypothesis testing, we have one of two outcomes. We could either reject the null successfully, that's what we wanted to do, right? We could either reject the null, or we could fail to reject the null. We don't call this accept the alternative, we don't call it accepting the null, sorry. We call it failing to reject, because that's how much we wish we could have rejected the null. We failed to reject the null, okay? Now let's think about these two decisions in conjunction with reality. Here's the thing. When we reject the null hypothesis and say, this sample did not come from this population, if it really didn't come from that population, we would be correct here. This would be a correct decision, right? If this was our decision and this is indeed the world we live in, this is a correct decision, right? If we failed to reject the null, however, we failed, right? We're like, oh, I can't reject the null, right? But the null is actually true. We shouldn't have rejected it. Then this also represents a correct decision. Good job not rejecting the null. The null was right all along, right? So these two are ways that we could be correct. That leaves us two ways that we could be incorrect. So one way is this. We could we could reject the null, successfully reject the null. But the null is actually true. We said, null, you are false. But the null is actually true. This is an incorrect decision, right? And not only that, but we call this a false alarm. Because we were all like, woohoo, we were rejecting that null. Pew, 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 get out of here, right? But false alarm, we shouldn't have actually rejected that null. And this false alarm rate, the probability of that false alarm, is going to be called alpha. It's represented by the term alpha. Now, on the other hand, there is another way, yet another way that we could be wrong. And that way is this. We could fail to reject the null. We could say, I don't know. The null may not be wrong. I don't know, right? We failed to reject it. But the null is wrong. It's false, right? And so this is also an incorrect decision, right? We weren't trigger happy enough, right? This is not called a false alarm. Instead, it's called a miss. Miss, right? And this we're actually going to call the beta rate, right? And so obviously the alpha and the beta have a probability of less than 1 but greater than 0, right? So what we want to do in hypothesis testing is reduce our chance of errors, right? We want to reduce our chance of errors. And we can also figure out what is our probability of getting different kinds of correct decisions. And because we know that this is one version of the world and that should add up to 100%, this probability of failing to reject when we should have kept the null around, right? This probability is 1 minus alpha. This is sort of what we call, this is sort of just my term, but like a correct failure, right? I mean, it sounds sort of odd, right? But it's like, it's good that you failed, you know? Like, you failed to reject it, and you should have failed to reject it, you know? That's okay. It's like, you failed to reject a date, and it's good. You know, that date was really good. He's a good guy, right? So, or a good girl. So, you know, you should have failed to reject him. Good, you know, something like that. So correct failure. On the other hand, this is another possible set of what could be right in the world. So this should add up to 100%. So this should be 1 minus beta. That's our rate of correct decision. Where we successfully reject the null, we say, get out of here. And the null is indeed false, right? So in dating, it might be you reject somebody, comes up to you, and good job, you should have rejected them. They're a total loser, right? Okay, so that's what we call a hit. Sort of like in Battleship, you said, pew, right? And you hit it. You hit it on the dot, right? So this is the hit rate. This is the miss rate. This is the false alarm rate. And this is just my word. This is the correct failure rate. All right, so now let's talk about the steps of hypothesis testing. Well, there are going to be 5 steps, and the first step just starts off with setting up your hypothetical population, right? So this is the hypothetical population, and you need to create both a null hypothesis and an alternative hypothesis. Then you want to pick a significance level. So you could think of the word significant as standoutness, right? Like how much it stands out. So how much does it have to stand out? When it stands out a lot, you have a very low false alarm rate, right? So if your X bar is just really out there, right? Then you have a small chance of false alarming. You're saying, you know, this really doesn't look like it belongs in this population because it's so out here. And that's why your false alarm rate is low. You want to set a low one. And if you want to be more conservative, you want to set an even lower false alarm rate. For instance, alpha equals 0.01, right? That would be even lower rate of false alarm. Then you want to set a decision stage. So far we haven't done anything except like setting things up yet. And still we're setting things up. We set up a decision stage. And what you want to do is draw the SDOM, the sampling distribution, right? So remember we have this hypothetical population and we create a sampling distribution so that we could take our sample and compare it to that sampling distribution. So you draw the SDOM and you identify the critical limits. So here's my SDOM. And you want to identify the extreme regions where you say, if your X bar is somewhere out here, right, then you want to reject a null. You reject the null. You want to say it's very, very unlikely to have come from this null population. And then you choose a test statistic because the test statistic will tell you how far out from the mean it is in terms of standard error, right? So how many jumps out you are. And that's and this will be called choose a critical test statistic. So you're saying, what are the boundaries that I'm willing to what are the boundaries, the extreme boundaries, such that if X is outside those boundaries, we reject it. If it's inside those boundaries, we don't reject. And then we use the sample. So this is the first time we're doing anything with the sample. We use the sample and the SDOM, right, from here, to compute the sample's test statistic and p-value. And the p-value is going to tell you, given that X is out here, how much of that curve does it actually cover? What is the probability of false alarming there at that particular value, right? And then you compare this sample to this SDOM population and you decide reject the null or not. So one word about p-value versus alpha, right? So the p-value is going to be the probability of belonging to the null population, right, given sample x bar, right? So what is the probability of that this value belongs in here? Alpha is what we call the critical limit. This is what we're able to tolerate. We just said it, right? And alpha is often decided just by the scientific community. In fact, alpha is often set to something like 0.05 or 0.01 because that's commonly accepted in scientific communities. We call that just being by tradition or convention, right? It's not that we figured out the alpha level. On the other hand, we figure out the p-value level given our sample x. And what we want is for the p-value to be lower than the critical limit. Okay, so now let's go through some examples. So here's an example of single sample hypothesis testing, also called a t-test of one mean, or single mean t-test. T-test with one mean. It might be one mean or single mean. I don't know. Same thing. So this is also another term for it. Let's talk about this when sigma is available. The population standard deviation has been given to us. So here it says the average Facebook user has 230 friends, sigma of 950. A random sample of college students, n equals 239, showed that the sample mean was 393 friends. Are college students like the average Facebook user? Well, let's try to think about this by using hypothesis testing. So the first thing is, perhaps we should set up the sort of standard, right, the standard population as the average Facebook user, right? So the real population of all Facebook users, right? So our null hypothesis might be something like mu equals 230, right? That the null hypothesis is that our college student sample is just like everybody else, right? The alternative hypothesis is that our sample does not come from such they're not similar to that population. All right, so now let's set the significance level. Here, we could just use alpha equals 0.05 by convention, right? We could say that's traditionally what's used, so we will use that too. Now let's set the decision stage. Here we want to start off by drawing the SDOM. And I like to label for myself that it's the SDOM, just so that I don't get confused and mistake it for the population or something like that. And we want to draw critical limits. If this is the only false alarm that we are willing to tolerate, then we might say, you know, everything out here we reject. And everything out here we reject, right? That would mean that everything in here is 95%. And out here, these two regions together add up to 5%. Because we're going to reject it, there's still some probability that this sample belongs to this population. But we're going to reject the null, right? And so here, we need to split up that 5% and distribute it to both sides. So this would make this 2.5%, and this would be also 2.5%, right? So that's the error that we're willing to tolerate. And I'll just color in right now my rejection regions, right? So that means if it's out here in the extremes, I'm going to reject my null hypothesis. And because we know that this SDOM comes from this population, right? That's how we're creating this SDOM. We know that the mu of the estimate is exactly equal to the mu of the population. So that would be 230, right? So mu sub x bar equals 230. But we can also figure out the sigma sub x bar, right? And that would just be sigma divided by square root of n, which is 950 divided by the square root of 239. And you could just pull out a calculator to do this. I'm going to just use a blank Excel file. So here's 950 divided by the square root of 239. So I get 61.5. Okay, so that's my standard error of this population. And what I want to know is, it's nice to have that, but it would also be nice to know, what is the z-score out here? We use z-score because we're using sigma, right? So what's the z-score out here? Actually, I had just made you memorize it when we previously talked about confidence intervals. So we know that's 1.96 and negative 1.96, right? But if you wanted to, you could also figure it out by using either the table in the back of your book or Excel. So we could put in norms inv because we have the probability, and I want the two-tailed probability. Oh, so maybe this is actually one-tailed. I should give it one-tailed probability. Ah, okay. So the one-tailed probability is going to be 0.025, so way down here, this little bottom part down here, it's covered 0.025 of this, and Excel is telling me that the z-score right there is negative about 1.96, a little bit less, but okay. So now that we have all of that settled, now we could start tinkering with our actual sample. So let me draw some space here. So now let's talk about our sample. So when we talk about our sample, we should figure out how far away is our sample mean, right? And we don't just want to know it in terms of how far away they are in terms of friends. We want to know how far away in terms of standard deviation, because only standard deviation will tell us what proportion of this curve is colored, right? And so let's try to, because even if we find out the actual raw distance away, 163, we don't know where that is in relation to this curve, right? So it would be nice if we could find the z-score of 393, because then we'll know where it is in relation to this curve. So that would be 393 minus 230, so how far it is away from 230, all divided by the standard error, 61.5, because that will give me how many standard errors away we are. And so let me just calculate that. So that would be 393 minus 230. I need parentheses because I need it to do the subtraction before the division. And that gives me 2.65. So my z-score is 2.65. So now I could draw it. So here, this is maybe 1 z-score away. This is almost 2 z-scores away. Let's say this is 3 z-scores away. I know that my 393 is somewhere around here, 393, right? Because it's around 2.65. Now, this area is very, 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 very tiny, very, very tiny. So I need to find the p-value here. So what's the p-value out here? So what is the probability that x is, or that x bar rather, because this is an estimate, it's a distribution of a whole bunch of means, that x bar is greater than or equal to 393? Well, that equals the probability that z is greater than or equal to 2.65. Not only that, but remember, we have a two-tailed hypothesis. We're interested in either being greater than or less than the mean, right? So we actually have to find this thing out and then multiply it by 2. So what you can do is look this up in the back of your book and then multiply it by 2. Or Excel will actually calculate it for you. You could put in norms dist and put in, I'll put in the negative side because norms dist gives it to me going from the negative side to the positive side. So it's going to color in this part first. So negative 2.65, and this should be a very, very small, tiny, tiny, tiny number. So that'll be 0.004. That's a tiny number. And then we take that one side and we multiply it by 2 to give us our p-value. So what we're really doing is, we're coloring this space, right? So pretend that's inside. And then also getting, negative 2.65. and coloring that space and adding those two together, right? And that will give us 0.008. All right. Okay, so what about a single sample hypothesis test when sigma is not available? Well, this is the exact same problem, except I have crossed this out, so you can no longer use it. Sorry, bub. It's no longer available to you. Here, what we're going to have to do is estimate sigma. So we're going to have to use S instead of sigma. So let's go ahead and start off just hypothesis testing. So our null hypothesis is mu equals 230, that our sample of college students is just like everybody else. Our alternative is that they are different from everybody else. Right? Different in some way, either have more friends or way less friends. We also need to pick a significance level. How extreme does this have to be? Does this x bar have to be? And we're going to pick alpha equals 0.05 just by convention. We didn't figure it out or anything. And then we need to set our decision stage. So here we want to start off by drawing our SDOM. It helps to keep this in mind that this is a bunch of means, a bunch of x bars, right? We can just use this information because this is our known population. We're going to use that information to figure out our SDOM. But here we run into the problem. How can we figure out standard error? Well, we can't figure out sigma sub x bar, but we could actually figure out S sub x bar, right? That's standard error using S instead of sigma. So that would be S, regular S of x, divided by square root of n. And so we have S from our sample. The standard deviation of our sample was 447. Divided by the square root of 239. And I will just pull up my Excel. I'll just pull up my Excel in order to calculate this. 447 divided by the square root of 239. And I get 28.9. Great. And I'm actually going to draw in my rejection region. So anything more extreme is going to be rejected. Reject, reject, right? Fail to reject in the middle, right? And this rejection region is 0.025, and this rejection region is 0.025 because I need to split that significance level in two. Okay. So what we do here is we want to figure out what is our actual t statistic, how many standard errors we are when we talk about these borders. What's our critical t? So that would be the t values here. So these are our raw values in terms of friends, but we want to know it in terms of standard error. So here's our t value. So we can't just put in 1.96 because that would be for z distributions. We need a t distribution. And in order to find a t distribution, we need degrees of freedom, right? And so the degrees of freedom is n minus 1, and that's 238 because 239 minus 1. So you could either look this up in the back of your book, or I'm going to look this up on Excel. So here I'm going to use my t inverse, and I put in my two-tailed probability, 0.05, right? And my degrees of freedom, which is 238. And I get 1.97, 1.97. So positive 1.97 and negative 1.97, because t distributions, as many problems as they have, they're perfectly symmetrical. Okay, so those are our critical t's. That's our boundary t values. Okay, now that we have all of that, now we could start thinking about our sample, right? So now let's think about our samples t and p-value. So the sample t would be the distance that our sample is away from our mean divided by standard error, because we want how many standard errors away we are. So 393 minus 230 divided by this standard error, 28.9. I'm just going to put that into my Excel. 393 minus 230 divided by 28.9. So that's going to be 5.664. Now let's find the p-value there. So we know that it's really far out here, our t-value. So if this is about 2, this is about 4, 5.6. I mean, it's like way out here, you know? Imagine this going all the way out here. That's where our X bar landed, right? So we're saying, oh, okay, already we know that it's pretty far out, but let's find the precise p-value there. In order to find the p-value, we want to use t-dist because that's going to give us the probability. We put in the x, that's Excel's word for t, so when you see x here in t-distribution, just put in your t-value, and it only accepts positive t-values. So 5.64, well actually I'll just point to this one. Our degrees of freedom, which is 238, and how many tails? Well, we have a two-tailed hypothesis, so we put 2. And we get 4.8 times 10 to the negative 8 power. So that would be, so our p-value equals, so our probability of getting a t that's greater than or equal to 5.64 or t is less than or equal to negative 5.64, right? Because it's two-tailed, equals 4.8 times 10 to the negative 8. So imagine 0.07 times 48, right? So that's a pretty tiny number, right? So this number is so small that that they can't even, show you all the decimal spaces. So it's so super close to 0, but not 0, right? So this is our p-value. Is this p-value less than 0.05? Indeed it is, right? So what do? We reject the null hypotheses, right? So this is what we do when sigma is not available. Let's talk, just to recap, about alpha versus p-value. So p-value gives the probability of seeing that sample t or an even more extreme test statistic given that the null hypothesis is true. And we say extreme because it could be like way bigger or way smaller, either side, right? And alpha gives you the level of significance, the level of extremeness that you have to reach in order to reject your null, right? So this is the set standard. And this is the thing that you are going to compare to that set standard. Now, I want to talk briefly about one versus two-tailed hypotheses. When we talk about a one-tailed hypothesis, you might have something like mu is going to be greater than 0, right? Or your alternative, maybe greater than or equal to, will be mu is less than 0, right? If that's the case, and your set alpha level is 0.05, then here's what you would do in your SDOM. You would only use one side of it because you're not interested if your x value is way up here. You're like, I don't care. I'm okay with that. You only care if your x value is way, way, way smaller than your population. So in this case, you might set up this as your rejection zone. And notice that it's only on one side because it's one-tailed, and these little ends are called tails, right? And that probability will be 0.05, right? And this fail to reject side will be 0.95, right? That's a one-tailed hypothesis. Frequently, we will be dealing with two-tailed hypotheses. And in that case, that might be that, you know what, we don't really care. We don't really care if mu is less than, way smaller than, or way bigger than what we expected. We just care if it's extreme in some way, if it's different in some way. We don't really care which way. And that would be mu equals 0. And the alternative is that mu does not equal 0. And if we have something like alpha equals 0.05 in a two-tailed hypothesis, then we would split up that rejection region into the two tails. So that would be 0.025, 0.025. We reject. But inside of these boundaries, we fail to reject. And this is 90.95, 95%. All right, so whatever p-value we find, we want to compare it to the set alpha level.